Hello and welcome to a new chapter, the first chapter in Machine Dynamics 2, a chapter that deals with journal bearings. So journal bearings are really perfect bearings because they include on the one hand the lubrication and on the other hand they provide the classical bearing properties, so they carry the load. Yeah? However, they always require the motion of the rotor, otherwise the hydrodynamic generation of pressure wouldn't be possible. And now the task will be to derive an equation. It will be a partial differential equation that governs this pressure field. And the derivation of this equation that governs the pressure field, the Reynolds equation, is quite involved. It will require 3 videos until the Reynolds equation is there. So maybe we think a little bit about what happens inside such a hydrodynamic journal bearing. There is an external force, for example the dead load of the rotor. Due to that external force, the shaft in the bearing reacts with the displacement. So it is displaced from the shaft center with respect to the bearing center. The shaft center and the bearing center will not be at the same point anymore. Therefore, there is a convergent part and a divergent part in this so-called lubrication gap where it is filled by oil. The oil is squeezed in the convergent part, so the pressure is positive, and in the divergent part it may expand, so the pressure, well, cannot become negative, that would be cavitation, but at least it drops down. And this pressure here that is in the convergent part then creates the restoring force that carries the rotor. This is the basic idea. Things become more difficult because such a rotor in a journal bearing, well, as I said, the motion of the rotor is necessary for hydrodynamic generation of the pressure. There's an S missing, I'm sorry for that, you had it. However, on the other hand, the pressure, the hydrodynamic pressure, influences, so there is a back influence on the motion of the rotor. And the influence could be such that the motion of the shaft becomes unstable. So hydrodynamic lubrication can lead to instabilities of the motion of such rotor. And this will be studied even in the next chapter. We will need a whole chapter to derive the Reynolds equation, to solve the Reynolds equation, to compute the bearing forces, the restoring forces, and then to linearize them and to get spring and damping coefficients. This is the subject of this chapter, and it is a subject of 5 videos already. 3 for the derivation of the Reynolds equation, 2 more videos to solve and to linearize the solution. So what is the coordinate system we are dealing with here? You can see the coordinate system right here. You can see that there's a lateral direction, it's the y-axis, and the x-axis is the vertical direction. There's the rotation, omega, and now there is a displacement of the center of the shaft, center of gravity also, with respect to the origin of that coordinate system, which is the bearing center. That displacement can be described by 2 coordinates because we are dealing here with a plane problem. You can see we are dealing with the xy plane here, and we are dealing with the rigid body assumption for that shaft here, at least for the cross section of the shaft we are dealing with. So we need 2 coordinates to describe that motion. There's one radial coordinate, it's called E here. It's now the eccentricity of the center of gravity with respect to the center of the bearing. For those that watch the videos in machine dynamics, I just make the remark that this has nothing to do with the eccentricity you had for the Jeff control tower. And then there is an angular coordinate, it's angle gamma here. Yeah. Okay, so these are the parameters that we are dealing with. And now the question is, well, how can we derive equations that govern the pressure field? So what kind of equations are there available for the pressure field? Well, the first equation would be the balance of mass, or the so-called continuity equation. The second one would be the balance of linear momentum for Newtonian fluids, long name for the Navier-Stokes equation. That would be the two equations we could use here, but there are even more equations. There is a thermodynamic balance, that way, so the energy balance, with a constitutive law for the heat flux. And finally, there is also the state equation for the determination of the viscosity as a function of pressure on the one hand and temperature on the other hand. And these last two equations will not be used here. Why? Because the influence of the temperature and pressure is somehow balanced if you look at the convergent part of that lubrication gap. In the convergent part of the lubrication gap, you have an increase of the pressure. You have an increase of the temperature there. And what happens to the viscosity, which is an important parameter in the Navier-Stokes equation, the viscosity term? The viscosity clearly is temperature dependent. Therefore, we need the energy balance, and therefore we need that state equation in order to, from the energy balance, to infer the temperature field. And from the temperature, we would be able to compute the viscosity. On the other hand, the viscosity is also pressure dependent. And what happens? If you increase the temperature, then the viscosity drops down. If, however, you increase the pressure, you increase the viscosity because you press your oil. No? What happens now in the convergent part of the lubrication gap? You increase the pressure and you increase the temperature. The viscosity would like to increase due to the increase in pressure and would like to reduce, so to be smaller due to the increase of the temperature. And if you assume that approximately these two effects balance, so that we get a kind of average viscosity from these two effects, then you can conclude that the viscosity is approximately independent on both parameters or on that situation in the convergent gap, because the convergent lubrication gap, because there's one effect that tends to increase the viscosity, namely the increase of pressure, and there is another effect that tends to decrease the viscosity, namely the increase in temperature. And therefore, these two effects will more or less cancel each other, and we do not consider the temperature dependence of the viscosity, and therefore we drop the last two equations. So we are left with the balance of mass and with the balance of linear momentum. That's even difficult enough. So we have to simplify these two equations, especially the balance of linear momentum will be simplified, will be solved then for the velocity field, and then the velocity field is introduced, as a solution of the velocity field is introduced in the balance of mass, and finally we obtain a partial differential equation that governs the pressure. Well, and this is then the Reynolds equation. So again, the simplifying assumption here are that we have constant viscosity. We are dealing with an incompressible fluid. So we simplify the continuity equation, and we deal with a small Reynolds number. So we neglect inertia and gravity with respect to viscosity. So We have two equations. The continuity equation, or divergence of the velocity, is equal to 0 for an incompressible fluid, and the Navier-Stokes equation, where due to the small Reynolds number assumption, we neglected the inertia terms and we just have a balance between the gradient of the pressure and the viscosity terms. Now in the next step, we have to write down these equations and transform them to our coordinate system. And as we are dealing with cylindrical bearings only, it makes sense to derive these equations, so these differential operators, for cylindrical coordinates, and to express everything in cylindrical coordinates. So the approach is then to simplify, so to express everything in cylindrical coordinates, simplify the Navier-Stokes equations there, solve the simplified Navier-Stokes equation, apply the boundary conditions for the velocity. These are the constants of integration for the solution of the simplified Navier-Stokes equation. Plug everything into the continuity equation. We will do something more. We will average the continuity equation in radial direction. I will explain that later on, even not in this video. And finally, we then deduce a partial differential equation for the pressure. Okay, so then let's start to write down the equations that we need, the continuity equation and the Navier-Stokes equation, in cylindrical coordinates. So for this we have to transfer the differential operators div, grad and the Laplacian to cylindrical coordinates. There's a nice theory that allows you to do this, namely it's called tensor analysis. Yes. For example, this is taught in mathematical methods in dynamics. There's an introduction to tensor analysis, and then you can define coordinates, curved coordinates. You can compute the so-called Christoffel symbols, and by means of these Christoffel symbols between the coordinate transformations, you are able to transform all the differential operators. But not everyone had access to a course in tensor analysis, and perhaps not everyone likes tensor analysis. So there is a much easier way. I would call it, it's by hand, so manually deriving these transformation relationships. And sometimes this helps because if you use such an abstract theory like tensor analysis, it's perhaps probably at the very beginning that you do some error and that you overlook these errors because you apply a big machine, a big mechanism to solve or to derive the expressions, and this mechanism is quite abstract, so you do not have access to what you are really doing, and sometimes it helps to do it stepwise and, well, manually, and that's what I would like to do. So first of all, I will start with the basic relationship between our cylindrical coordinates and Cartesian coordinates. However, considering cylindrical coordinates would be even exaggerating, because for cylindrical and Cartesian coordinates you know quite well that the z direction is the same. The z direction is our axial direction, and only for our cross section, so for x and y, we transform between then polar coordinates r and phi and Cartesian coordinates x and y, and the z-axis is nice, but everything related to the z-coordinate is copied because it's the same coordinate for cylindrical and Cartesian coordinates. So there's a classical relationship between r and phi and x and y. X is equal r cosine phi, y is equal r sine phi, and you can invert that relationship, and then you get the radius as the square root of the, by Pythagoras, of the Cartesian coordinate squared and summed, and finally phi is just the arcus tangent of y divided by x. Now, if we want to derive something like a differential operator, we are dealing at least sometimes with vector quantities, and that's for sure here the case. The gradient would be a vector quantity. The divergence of a, for example, velocity field or some vector quantity would include at least a vector. So it's good to know the relationship between the base vectors of the Cartesian coordinates and of the polar coordinates. That has been dealt with in detail in engineering mechanics 3 or 4, and the relationship is shown here and can be deduced from the drawing. You will find the base vector in radial direction here, E sub r, and E sub phi in circumferential direction there. The classical Cartesian base vectors are E sub x and E sub y. And if we now look at E sub x, then it's ER projected by a cosine phi. Phi is that angle, so we start to measure our angle at the x, starting from the x-axis. You can see that ER cosine phi is the contribution from the unit vector E sub r on E sub x. And finally, E sub phi points opposite, the projection points opposite to E sub x, so taken with a negative sign, and you take the sign projection here to get the contribution on the x-axis. For the second equation, for E sub y, we also start with E sub r, and we have to take the sign here, contribution, of so sine phi times ER in EY direction, and from the second vector E phi in circumferential direction, we get the cosine projection. Okay. So next we have to compute the partial derivatives of our coordinates. So we compute the partial derivatives of r with respect to x and with respect to y. So the partial derivative of r with respect to x would be, from this expression here, 2x divided by 2r, which would be x divided by r. But this is not a nice result because we want to express everything in polar coordinates. So therefore we have to replace the Cartesian x here by its polar variables r cosine phi. Then we can even divide by r, or 2r, the whole expression, and at the very end we just get cosine of phi. We also need dr by dy. The reasoning is the same. So from taking the derivative of the square root expression, we get 2y divided by 2r. We replace y by r sine phi, and we end up with sine phi as being the partial derivative of r with respect to y. Finally, we have to do the same for the angle, which is a little bit more involved because we have to take the derivative of an arcus tangent. But this is clear. It's here given by 1 divided by 1 plus y divided by x squared. There's an inner derivative, which is minus y divided by x squared. So the total derivative of that expression is minus 1 divided by 1 plus y divided by x squared, y divided by x squared. Again, here we have to replace now all the y and x, so all the Cartesian variables, by polar coordinates, by r and phi. And you can see if we do this here, then we get just, again, the angle here. And so here we would get sine phi divided by cosine phi square. We multiply the whole expression then by cosine phi squared. So then we get cosine phi squared plus sine phi squared, which yields 1. So we get a minus cosine phi squared. For the x squared, we have r squared cosine phi squared, so the cosine phi squared cancel. And by replacing in the numerator the y by r sine phi, we get in total minus sine phi divided by r. Same can be done with respect to y. So again, for the exterior derivative, or for the derivative of the arcus tangent function, we get 1 divided by 1 plus y divided by x squared. And now the inner derivative is a little bit simpler. It's just 1 divided by x because you take the derivative with respect to y here. Again, you replace every y, every x, so every Cartesian coordinate by polar coordinates. You multiply in order to get a nice expression here for the first term. You insert, you multiply the numerator and the denominator by a cosine squared to get cosine squared of phi. For 1 divided by x, you insert r cosine phi, so you get cosine phi divided by r. Here it is. Okay, I copy the results to the next slide, and then we will try to manipulate the differential operators, and I will show you just one example here. So these are all the results we need. Well, and of course the relationship between the Cartesian and polar coordinates as well. So we need the partial differentials, and we need here the base vectors and the representation of the base vectors, and then we start with the divergence of a velocity field, just as an example. And you can see that for the gradient and for the Laplacian it works as well, but I wouldn't go too much into technical details, just present you then the results for the other two differential operators. So what can you see? Well, the divergence is computed by just taking the individual Cartesian coordinates of the velocity vector and taking the corresponding partial derivative and then adding everything up. If we want to transfer this result to Cartesian coordinates, what we have to do is we have to transfer each of the differential operators, and we have to transform also the vector components. These Cartesian vector components, they are obviously obtained by multiplying the velocity vector v by a scalar product with the appropriate base vectors. I could call this, of course, also I project the velocity vector on the base vector, and this projection is done by the scalar product, by the dot product with the appropriate base vector. Now, as you can see, I can replace the base vector e sub x by e sub r cosine phi minus e sub phi sine phi. Therefore, for vx, I could write the product of v with the base vector er times cosine phi minus v velocity vector multiplied, scalar product with e sub phi, sine phi. And these projections now on r and phi of the velocity vector are then called v sub r and v sub phi, and are the corresponding coefficients or coordinates in radial and circumferential directions. And that's what we want to see here. Yeah? So two tasks: replace v sub x, v sub y, and v sub z by taking into account these projections on, or introduce the new coordinates of the velocity vector, namely in radial and circumferential direction, and transform these differential operators, these derivatives. Here this is shown for the first term in the divergence. You can see again, if we look at v sub x, and v sub x is obtained by multiplying the velocity vector by ex, you can see that this is exactly what you would get from the right hand side of e sub x, namely you get the projection on e sub r, or v sub r, and you get the cosine of phi here. Well, this. Yeah. Finally, for the second term, you get velocity vector times e sub phi, which yields then v sub phi, and you have the sine phi. How about the operator here? Well, this is the classical application, you could say, of a chain rule. So instead of having d sub x, you take into account all the other variables. So dr by dx, d by dr, plus d phi by dx, and d by d phi. And for these partial derivatives, we have obtained already the corresponding expressions. Let's move now. This is not yet the divergence, it's just the first term. So let's move now to the second term. We do the same. So again, well, if you look at this term here, it's obtained from the multiplication of the velocity vector with E sub I, namely this yields V sub y. So we get V sub r sine phi, here it is, and we get V sub phi cosine phi, here it is. And for the derivative, we now get the derivative of dr by dy, d by dr, d phi by dy, d by d phi. So the same as here, but you exchange the x to a y. And then finally there's a last term, and as you can see, that last term is just copied. In the next step, we insert the expressions we obtained for dr by dx and so on. So this yields, for the first term, again, a cosine of phi, here it is. For the second term, d phi by dx minus sine phi divided by r, here it is. Vr cosine phi minus v phi sine phi. Second term, we get for dr by dy a sine phi, here it is. And we get for d phi by dy a cosine phi divided by r, cosine phi divided by r. So everything is there, the rest is copied, and also the last term is copied. Well, now you see that there are some terms including derivatives with respect to r, with respect to phi. There will be also some other parts. So now we have to, well, sum up everything and collect our result. And what you see, if we do this, we have to pay a little bit attention, because not only the velocity components, Vr and V phi, depend on r and phi, but of course also the trigonometric functions, cosine and sine phi, depend on the angle phi. So one has to deal a little bit with care. So let's try to collect the results. And let's do this in a clever way, because as you can see from the first and the second line of that equation, there are many places where corresponding terms occur. So for example, if you take the derivative of Vr with respect to r, you can see that here you get cosine phi squared, while in the second line you will find a corresponding sine phi squared, and then of course due to the trigonometric Pythagoras this leads to 1, so you can combine these two terms to just dVr by dr. This would be our first term, and as you can see, I've made no use of the first term here and the first term there. Let's move forward. Let's move to the next term here. So, as I said, there's a possibility that we take the derivative of the cosine function here. Well, if we would take the derivative of d by d phi with respect to Vr, we would first get minus sine phi cosine phi divided by r. And we see that in the second equation we would get, if we do the same, if we apply the differential operator to v sub r, we would get cosine phi sine phi, so again a mixed term divided by r, but with an opposite sign. Here the sign is obviously negative, here it would be positive, so both effects will cancel. So once we have dealt with the derivative of the cosine phi and of the sine phi with respect to phi, we have completely dealt with the first term here. So applied all the differential operators to the first term in each of the parentheses. So what will be this expression? Well, you can see the solution here, but let's have a look at it. So you take the cosine phi with respect to phi, the derivative will be minus sine phi, so you get a plus sine phi squared here. And here we will take the derivative of the sine phi, it's a cosine phi, so you get a cosine phi squared. If you sum up everything and apply the trigonometric Pythagoras, you will get v sub r divided by r. And the interesting thing is, yes, that's indeed correct. It's a term that does not include any partial derivative. in contrast to what you learned about the divergence of a vector field. This expression does only hold in Cartesian coordinates. So in Cartesian coordinates, you have the sum of the partial derivatives, corresponding partial derivatives of every component. If you transform these results, for example, to polar coordinates or to cylindrical coordinates, you can't be sure that you always get these partial derivatives. There could be some other terms as well, as you can see here, even terms without any derivative. So now let's move to the second part. And as you can see here, for the first operator, if we apply the derivative d by dr, where we have the only opportunity to apply it is v sub phi, you will get a mixed term, cosine phi and sine phi, and you hope that this will cancel, and indeed it will do so. If you do the same here in the second line, you get a sine phi and a cosine phi, and the differential operator d by dr is applied to v sub phi. But the sign in the second line is different from the sign in the first line, so the two effects will cancel. So we move again to that term here. We take the derivative with respect to phi, and we have two possibilities again to apply it. We can apply it to v sub phi, which then yields a sine squared phi. Looks nice, looks like a trigonometric Pythagoras. And here you get a cosine squared phi. And this would be then the corresponding term. So you apply the derivative to v sub phi. You have a trigonometric Pythagoras, so you can leave all the trigonometric function out of consideration, and you get a 1 divided by r here. Well, and finally, we have to apply the derivative to the sine phi and to the cosine phi. But again, you can see that this leads to a mixed term with opposite sign, and this effect will cancel. So we just have to copy the last term, and here it is, our divergence operator, expressed in polar or cylindrical coordinates. So let me repeat the important steps. So first, there's some work to do. Namely, you need the transformations between the two coordinates, Cartesian and whatever else. Here, for example, cylindrical. You could also take spherical or whatever coordinate system you like. You need also the transformation of the base vectors. You have to compute all the partial derivatives of your new coordinate system with respect to the Cartesian coordinates. You start with a differential operator noted in the classical format, but in Cartesian coordinates. You have to transform the entities, if these are vectors, the vector components, by making use of the unit vectors, so by replacing the Cartesian unit vectors by some other unit vectors. And finally, you have to transform the differential operators, the derivatives, by making use of chain rules and by inserting the results that you previously computed. And finally, you have to add up everything and sort all the terms. And this could be also done by symbolic mathematics, of course. It's a nice topic for symbolic mathematics. Okay, now what's missing is the gradient operator and the Laplacian. For the gradient operator, well, maybe you can guess a little bit the results, but because you can imagine that you have dvx by dx, dvy by dy, and dvz by dz, or you have a scalar quantity dp by dx, dp by dy, dp by dz for pressure, with the same derivatives as here. So the reasoning comes quite close to what we have done here. So you can see here the gradient p, and you get dp by dr e sub r, 1 divided by r dp by d phi, and dp by dz. And for the Laplacian, the result is even more involved. And what you can see here is just the projection of that Laplacian in a radial direction, in circumferential direction, and in z direction, which indicates the three Navier-Stokes equations you will get in cylindrical coordinates from the balance of linear momentum. Yeah, we will consider the Navier-Stokes equation in radial, in circumferential, and then in z direction. And you can see, for example, for the pressure gradient here, that you would have to equate that first term to mu times the first line here, the second term to the projection of the Laplacian times, of course, the viscosity in circumferential direction, and the third term with that contribution in z direction. And of course, you have to also to multiply with the viscosity. Well, this is the first step. We do have now the, or we are able to formulate the divergence of the velocities equal to 0 and the Navier-Stokes, simplified Navier-Stokes equation without inertial effects in cylindrical coordinates, but we are not able to solve the Navier-Stokes equations in cylindrical coordinates, and therefore we have to simplify everything. And this simplification is done in the next video. Thank you very much for watching.